Hello there, my name's Richard Arundal and thank you very much for watching this video. Today is another lecture in the On-Orbit Manufacture series, and this time we're going to be looking at lasers as a potential manufacturing method. So grab yourself a nice brew, get yourself comfortable, and we'll begin. In this lecture, we're going to first revisit the top-level technology roadmap that we covered in the first video, Introduction to On-Orbit Manufacture. There's a link below if you want to revise that. We're going to have a brief introduction to the potential manufacturing techniques that we could consider for on-orbit manufacture. We're then going to narrow down into lasers and laser welding and cutting. We're going to talk about the theory of what a laser is at a very top level, the laser cutting and welding process theory as well. Then we're going to bring it all together and discuss how we could use laser manufacturing for on-orbit manufacturing. And then finally, we'll summarize and recap the lecture. On this slide, we can see how the manufacturing method fits into the larger technology roadmap. This roadmap diagram is covered and discussed more in the first video of the series, which is Introduction to On-Orbit Manufacture. For this video, let's take a sidestep now and explore some of the manufacturing methods that we could consider for on-orbit manufacture. We can see now on this slide that some of the manufacturing methods that we could consider for the space environment include lasers, forming, welding, adhesives, fastenings, and 3D printing. All of these methods have advantages and disadvantages along with their own associated theories of how they work. In this video, however, we're going to focus on the laser manufacturing method and essentially what applications we can look at. We're going to cover the top-level theory and its advantages and disadvantages, and then look at how we can apply it for on-orbit manufacture. The other methods we will cover in future videos in this series. Lasers are used in a wide variety of applications in industry. Such techniques involve cutting, surface ablation, marking, hardening, welding, brazing, drilling, and interferometry. There's a lot of different laser applications that we could see here, but for this video we're going to focus on the cutting and welding processes. You may have seen laser welding and cutting in action, maybe through films or from your school or other education, or perhaps you even work in an industry that uses lasers. But let's cover now the top-level theory of what a laser does and how it actually works. The word laser is actually an acronym for Light Amplification by Stimulated Emission of Radiation. A typical laser consists of three fundamental elements, which is your energy source or a pump, a lasing material, and some form of oscillator or cavity. Working through each of these three fundamental elements then, first of all, the energy source, which we refer to as the pump, can be considered the initial input of energy into the laser system so that there's an interaction with the laser medium. The lasing medium is composed of atoms whose energy levels are used to increase the power of a light wave as it travels through the laser system, and this is important because it will determine the output of the laser beam, which we will come on to shortly. The third element in a laser system is the oscillator or cavity, which in this example in the diagram we could see it's essentially two mirrors. So imagine now that the pump and the source provides energy into the system in the form of a light wave. This light wave then travels through the lasing medium and gathers energy, and as it exits through the medium to the other side, it will come into contact with the mirror and therefore oscillate through the system. Now, as it rebounds back through the medium, it will again gain more energy. So this cycle will repeat many times in a fraction of a second. So now that we have these light waves bouncing around the laser medium and between the mirrors, we want a useful output. So how do we achieve that? Firstly, one of the mirrors in the laser system will have a filter in it which will filter out undesired wavelengths for the output laser beam. The filter and the lasing medium therefore work together to create the desired output. This output wavelength is therefore a critical parameter and something we'll come back to in a few slides' time and see how it fits in with laser welding and cutting. I want to briefly interrupt the lecture here just to mention that the laser theory that I've just covered is grossly simplified, and it's a fascinating and very complex field, and it's going to be a future lecture that I'm going to work on to cover it in much more detail. So if you want to see that video and be aware when it comes out, hit that like and subscribe button and the little bell. You'll get a notification of when I get it uploaded. Anyway, let's carry on with the lecture. Now that we have a very top-level understanding of how a laser works, how does it fit in with laser cutting, and how does it all come together? In the diagram on the slide now, we can see that the laser emitter is where the light would be coming from in terms of the filtered wavelength. This output laser beam from the emitter is then likely to be reflected in a series of mirrors throughout a laser system so that we can get the energy to where we want it, i.e. the end of a work nozzle. And before we get to that, we'll go through a focusing lens. The purpose of the focusing lens is to converge all of the light waves coming from the laser emitter into a very small point. You may have noticed this when using a magnifying glass, for example, with the sun or perhaps another form of light, and you'll see that it will all concentrate into a very small point, and therefore that's where you get a high density of this energy. This focus point is more accurately referred to as the focal spot, or the spot size of a laser. With all this energy focused on a very small spot, what we find is that the power density is high, and this therefore leads to rapid heating in the target material. This means that for laser cutting, the workpiece is heated above its melting temperature and will lead to partial or complete vaporization. If we recall on the previous slide, we discussed wavelengths and how that's an important consideration for laser cutting and welding. For laser welding and cutting to be optimal, the wavelength should be matched with the type of material that will be the desired workpiece. On this graph, the left-hand side shows the material absorption percentage, with higher being more absorbable and lower being less absorbable. The bottom numbers represent the wavelength. Using aluminium as an example, and aluminium on this graph being the letters AL on the left-hand side and is the dark blue line, we can see that in the low wavelength bands, around 100 nanometers, we can see its absorption percentage is quite high. And as you go higher up the wavelength, you could see aluminium drops off very rapidly, and it doesn't rise up again to reasonable absorption rate until about the 1000 nanometer mark, which is represented here by the red dotted line going up and down the graph. If we were therefore to consider laser welding or cutting with aluminium, we would want to pick a laser that's either in the low wavelength band or around the 1000 nanometer band for optimal performance. The important lesson here then is that the wavelength absorption of a material should match the laser output that you're after, because otherwise the energy won't be absorbed properly by the material and therefore the heating won't occur as rapidly or perhaps even at all. So now that we've covered laser cutting, let's take a look now at laser welding, and we will see that there's a lot of similarities between them. With laser welding, what we want to do is to raise the temperature of the material workpiece in a similar way to laser cutting. There are two main types of laser welding, and that is conduction welding and keyhole welding. In conduction welding, we want to raise the workpiece to above melting temperature so that it creates a molten layer. When you bond two workpieces together to form the weld and join them together, this molten layer therefore all mixes in together between the two different pieces of material, and when the material then cools down and this molten layer resolidifies, that is when you've achieved your weld. Typically with conduction welding, the welding depth itself is fairly small, typically a few millimeters, and you often get a much wider weld and therefore a larger increase in the heat affected area. What you do find though is that you often get smooth aesthetic weld finishes, and therefore this is quite good for thin workpieces like foils and so forth. Keyhole welding, on the other hand, is typically used when you have thick pieces of material that you want to weld together. The power density to achieve much deeper penetration in the weld requires a much smaller spot size for the laser, and therefore what you find is that the weld will typically be much more narrow than the conduction welding. As keyhole welding seeks to achieve raising the temperature of the workpiece so that it vaporizes, you typically also require more power than conduction welding. And what you will find is that plasma tends to form if there's inefficiencies or there's too much power, and what happens then is that this plasma that forms around the keyhole will actually absorb some of the laser energy, which in turn reduces the efficiency of the weld process because it's not reaching the material properly. And as we learned in the previous slide about material wavelengths and absorption, this is a key consideration in laser welding. Let's move on now and discuss the advantages and disadvantages of laser cutting and welding. Starting with laser welding, it can easily be automated as part of a production line, and this automation therefore leads to consistent weld quality. With this automation and consistent welding, it means that even complex programs can carry out their work rapidly, and therefore this leads to potential savings because there's less scrappage and rework because the accuracy is potentially so high. Because of the physics involved with laser welding, the weld bead itself will be quite narrow in the order of millimeters, and this means that not only does it look better in terms of aesthetics, it allows laser welding to be carried out on small workpieces. Another advantage of having a narrow weld bead is that there is less distortion to the workpiece because of the heat process and the physics involved in laser welding. Laser welding produces high quality and high strength welds, and there's also potential for some flexibility to change the laser beam itself, the optical parameters and so forth, although that depends on the material and the hardware that is being used. Moving on to the advantages of laser cutting, there are a lot of similarities with laser welding. For example, the high work speed potential, the low distortion because of the smaller heat affected area, or has, and also the precision and the consistency of those results. Laser cutting performs well in both simple and complex workpiece handling. For example, a simple workpiece could just be a straight two-dimensional piece of material that is cut through, or if there was more complex robotics and programming of the robot arms and so forth, then you could also laser cut complex pieces of material into all sorts of different geometry. The last advantage of a laser cutter that we've got here is that we don't always require an edge to actually start the cut. So say for example you can imagine a pair of scissors and you're cutting paper, you have to start at the edge typically and then you cut the shape that you desire. With a laser cutter, the origin can start anywhere that is desired, and it achieves this by turning the power on, if you like, and applying the laser beam to the workpiece. But rather than moving to carry out the pattern, it might dwell there for a small amount of time so that a hole is created, and then through this hole it can then continue with the pattern of the cut. Let's explore now some of the disadvantages of lasers. As we discussed earlier in this video, the absorption of energy from the laser to the workpiece material is important, and so compatibility with the laser wavelength and the material of choice is important, but can lead to wider system incompatibility. Typically, laser systems are not very efficient, approximately 20 to 30% in terms of electrical power coming in to the laser power that you can generate. This is an important point to consider in the next slide, where we look at how we can apply lasers to on-orbit manufacturing. Laser systems can also be quite expensive in terms of the upfront hardware costs, and because of the nature of the components involved in the laser process, the electronics and the components can be quite fragile. So far in this lecture, we've talked about laser theory, we've talked about the cutting and the welding processes, and some advantages and disadvantages of lasers. Now we're going to put that all together and talk about how it can apply to on-orbit manufacture. Here we can see a diagram of an example concept with laser welding being the manufacturing method. If you are interested in seeing how this concept comes together in the first place, then please check out the first video in this lecture series, Introduction to On-Orbit Manufacture. So with the previous slides where we've talked about lasers and the theory, cutting and welding, let's think about what opportunities and challenges present themselves. The first opportunity to consider is the vacuum of space. Now, there's lots of literature that suggests that a vacuum and laser welding in particular actually performs at better efficiency, and I'm not going to go too much into the technical detail here, but in the description of this video I've linked some literature that I've used and drawn upon for my own research, should you wish to look into this more further and on a much more technical level. A simple top-level explanation of why a vacuum helps with laser welding, especially keyhole welding, is that the plasma formation that we discussed in the previous slides, this is suppressed in a vacuum, and so because there's less of a plasma field and plasma cloud in fact formed, this means that more of the laser energy can reach the workpiece and therefore heat the material and continue with the welding process. Another opportunity for lasers in on-orbit manufacture is that for tooling there isn't a contact, as it were, compared to other methods, so there's less chance of clogging or interference or mechanical jamming in that sense, but there are some other considerations which we'll talk about in the next section. As part of the laser welding and cutting process, we found that we have to raise the material's temperature in order for it to either melt or vaporize. So what about using the sun itself then to actually provide a passive form of preheating the material so that less energy is required to change from a temperature up to the melting or vaporization point? There are some challenges, however, with this preheating of the material idea, which we will come on to shortly. And last but by no means least, automation of lasers is obviously very beneficial, and lasers are very well suited for this, and so we could look at robotics and pre-programming, and that would do very well in the space environment. Let's think about the challenges then for using lasers as part of on-orbit manufacture. The first challenge to consider is the power subsystem of the actual spacecraft, as in the on-orbit manufacturing facility. Depending on the type of spacecraft and its mission, generating power is often tricky, not so much in a technical sense, but more the ability to generate large amounts of power. Laser systems typically require a lot of power to operate, even in large factories on Earth, so having a reasonable power system to support a laser in space will certainly be difficult, and this is where a lot of the challenge will lie, and where some of the opportunities would have to be explored or even maximized to help support the power aspect of lasers in space. Unlike what you may have seen in popular sci-fi films, lasers in space is not actually all that common. There's plenty of prototypes and work being done, and new missions are looking at communications which will use lasers, but at the moment that's something that needs to be worked on, and so we have a lack of hardware heritage, which means that because lasers aren't really used that much at the moment, there's not a lot of confidence in the system, so it will most likely take quite a few more years and lots more demonstrations and proof of hardware before a concept could be more fully developed and supported. Contamination is another challenge that we have to think about with laser processes, and contamination on, for example, the laser lenses or even the molten material from the laser process or spatter would certainly be an issue. If you can imagine random blobs of molten material being ejected from the workpiece in random directions due to the weightlessness of space, then you could perhaps consider and imagine the problems that this would cause. Engineering analysis, therefore, would need to consider this and design accordingly to mitigate or even entirely prevent it. One opportunity we looked at was the potential for passive material preheating, as in, let's say, use the sun to heat up our material so that less energy is required and therefore supports the laser processes. However, thermal cycling during orbit is a problem, especially if you imagine a low Earth orbit where a satellite would go from a day and then night cycle during its orbit quite rapidly. If you imagine this day-night cycle and the spacecraft as its orbit it is transitioning from light to dark, in the light side, as in facing the sun, temperatures could reach over 100 degrees Celsius in low Earth orbit, whereas on the shadow side it could be well over minus 150 degrees Celsius. What happens then is that when the transition occurs, the temperature will change, either getting hotter or colder reasonably rapidly, and this leads to something called thermal shock in materials. Thermal shock can be considered a mechanical load, and what happens is that you've got some parts of the material will be colder and some will be hotter, and so you'll essentially get different expansion in different parts of the material, and this can cause stresses and, in worst case scenarios, failure, as in fracture and cracking. From a laser system standpoint, this thermal cycling is also a problem, because if you try to carry out a manufacturing operation on very cold material, you would require more energy to raise the material to its melting point and vaporization, and if the laser isn't able to adapt to that power, for example, or it's not been designed for, then you won't be able to achieve your manufacture and your laser weld or cut. So timing, therefore, of these processes would need to be considered as part of the mission design. The material selection for use in on-orbit manufacture would also have to be considered, not only for the space environment and its appropriateness, but also its suitability for the laser processing itself. Finally, let's consider then the fragile hardware that makes up a laser system. Components like the lenses, for example, all have to be finely tuned so that the spot size of the laser and of course the mirrors and the pumps and the electronics and so forth all have to be carefully calibrated, so the violent environment of launch, for example from Earth into space, can be designed for so that the laser system survives and can operate in space. So let's recap what we've learnt today in this lecture. We had a quick revisit to the technology roadmap from the very first video, On-Orbit Manufacturing Introduction, and we could see how lasers fit in the whole potential manufacturing techniques, and we've looked at some of the theory as well for both cutting and welding using lasers, and we've also looked at how manufacturing could be used in the wider facility and in space environment, and thought about some of the challenges and some of the opportunities. So that concludes today's lecture with lasers in on-orbit manufacture. So this entire series that I've got planned, there's going to be a lot of videos, and a lot of it is going to touch the very top level concepts before going much deeper into the detail. But if you want to follow along in this journey, then hit that like and subscribe button and the little bell, and you'll get notified when new videos come out. There's so much to cover, and I'm really looking forward to showing and presenting the research to everybody. So until next time, thank you very much.